Our next speaker is Robert Nairn. He's a professor in the University of Oklahoma School of Engineering and Environmental Science, director of the Center for Restoration of Ecosystems and Watersheds, director of the Water Technologies for Emerging Regions Center, and an adjunct professor in biological sciences. His presentation today is Natural Infrastructure Approaches to PFAS Pollution, examining treatment at wetland mesocosm performance to support indirect potable reuse efforts.
Okay, before I begin, I want to be very clear that I am not a PFAS expert like the rest of our speakers this afternoon. I'm a wetlands guy, a biogeochemist, so my expertise in this area is limited. I'll do the best that I can. I also want to thank Ann Briggs for her understanding. I had some health issues that were questioning whether I'd be here, and she's been very understanding and very helpful to make sure that this all worked out. I'd like to acknowledge all my co-authors, Lynn Wen, James Queen, Livia Overton, and Zach Cassidy, who's sitting right here. All my co-authors are graduate students in CREW, the Center for Restoration of Ecosystems and Watersheds at OU. And they're really the folks that have done the majority of the work that I'll talk about today. Before I begin, I want to acknowledge that OU, the University of Oklahoma, resides on the traditional home of the Caddo Nation, the Wichita-affiliated tribes, and served as a hunting ground for several other Native American nations. Today, Oklahoma is home to 39 Native nations as a result of removal policies. As I said, I want to talk about wetlands. And wetlands are kind of my ecosystem of choice. They are absolutely astoundingly diverse and unique ecosystems. So a lot of things can go on in these systems, and we've been able to exploit that kind of natural biogeochemical diversity by building treatment wetlands to address surface waters. Oop, there it goes. Yeah. And that's what the two projects that are interrelated I'd like to talk about today. One was an NSF EPSCoR project. It's a Socially Sustainable Solutions for Water, Carbon, and Infrastructure Resilience, or S3OK. And then we coupled the work that we were doing with the NSF work with a Bureau of Reclamation grant on wetland mesocosm studies supporting integration of water reuse and stormwater management. S3OK is a really unique approach. Kevin Wagner was here earlier. He is actually the PI at Oklahoma State University on this work. He had to head back to Stillwater before I could speak. But really the focus of S3OK is this idea of wicked problems. There are four related but different approaches that are being taken. It's a big effort. It's multiple universities. It's $20 million over 5 years. It's a big deal. So what is this wicked problem idea? It's where we have incomplete knowledge or competing understandings, interconnected problems with stakeholders and institutions might not be interconnected, lots of different perceptions and beliefs and interests, and where the economic costs can be large and equally distributed. The idea of sustainable solutions is to really try to develop and address all those questions, finding these solutions at the intersections of these related but distinct problem areas. So it's been, for me, a very enlightening approach, working with social scientists very closely that we never had in the past. But I guess the question you might be asking is, what the hell has that got to do with PFAS, right? Well, it's a PFAS session. We should be talking about that. Well, PFAS is a wicked problem. It's a wicked problem that needs to be addressed. There are traditional resource and energy intensive technologies that certainly show promise. And I think our other speakers this afternoon are doing a great job of pointing those out. What we have been thinking about are this idea of nature-based solutions that might be economically and environmentally feasible to address PFAS. Again, traditional infrastructure approaches like the water reclamation facility in the city of Norman, where OU's at, don't necessarily do a good job with these emerging contaminants, but can be modified. And there's active work going on with the city of Norman to address things like PFAS through active technologies. Our work focuses on this little area right here. This is our treatment wetland mesocosm compound. Just near the effluent of the wastewater treatment plant. This is a traditional secondary, or excuse me, a activated sludge treatment plant. So this is secondarily treated effluent. The alternative is to think about an idea like this. This is the East Fork Raw Water Supply Project in Combine, Texas. One of the largest human-made wetland ecosystems in the United States, which draws effluent-dominated river water from the East Fork of the Trinity and treats it and discharges it back into the drinking water supply reservoir upstream. Okay. Why is that important? Because there's a lot of cool stuff that goes on in wetlands. They can mineralize, they can sequester things in the deep sediments in the peat and the living biomass, but that orange line there is the redox interface. So we can have very diverse redox reactions occurring in close proximity to one another. And in some cases, these systems are sinks, they might be sources, they might be transformers, and they've been exploited over the last several decades to we've been able to build these systems to address traditional constituents. The question is, are they sources, sinks, and transformers for something like PFAS? They can be. So this is a diagram from one of Olivia's papers from a couple years ago that identifies some of those mechanisms that may affect these emerging contaminants within the wetland environment. And again, a lot of this is based upon the close proximity of that redox interface. This is especially important in a place like Norman, Oklahoma. So why are we doing this here? Our drinking water reservoir is Lake Thunderbird, out east of town. There it is during the 2013 during drought conditions, in 2015 during a flood. Oklahoma has passed the Water for 2060 Act a few years ago that says we're going to consume no more fresh water in 2060 than we did in 2010. The comprehensive water plan is currently being updated, really forecasted future water shortages, and one of the recommendations is reuse. So stormwater reuse, wastewater reuse to address our water challenges. Of course, there are now national primary drinking water regulations for some of these compounds that we need to consider when we start thinking about reuse. When I moved to Norman in 1997, we were a little less than 90,000 people. We're at 130,000 now, and by 2050, the projection is that we'll be close to 200,000. Lake Thunderbird's not getting any bigger. We got to think about where we're going to get our drinking water over the next couple decades, and reuse is one of the things that we're interested in. That's from our comprehensive water plan, freshwater use on the left-hand side, the percent reduction that's necessary to reach that water 2060 goal. You can see somewhere around 30% statewide. Okay, so our partners with the Norman Water Reclamation Facility, the city of Norman, have been tremendously important to getting this work done. Again, there is our activated sludge plant. You can see the white rectangle at the bottom is our mesocosm compound. There we go. The nice thing about that location is that we have access. I'll go back real quick. Just above the Norman. What did I do? I guess you can't go back, can you? Okay. We are right. We have a stormwater drainage that actually goes right by our effluent. So we have ready access to both secondarily treated wastewater as well as urban stormwater. Matter of fact, it's dominated by the university. So a lot of parking lots, a lot of rooftops, pretty typical urban stormwater. And I don't know what I can keep talking about. So we'll get there in just a second. So we've got access to that. We developed a plan of action under the S3OK project that we then, there we go. Yeah, so you can see that kind of stormwater is that horizontal line across the top of the city of Norman symbol there. That's our urban stormwater coming from the university. So that's north of our compound. These are our mesocosms. There's our treated wastewater effluent on the right-hand side. The idea of this system was to be able to draw both of those sources of water, two separate different sources of water, and evaluate them. We have multiple designs. I'll show you in just a second what those are. They're planted by, as you can see, our hardworking students out there, keeping our wetlands going. We sample them on both a regular basis, but also through a series of experiments that I'll talk about in just a second here. So 2 different source waters, a couple different hydraulic designs, free water surface or surface flow, subsurface flow, as well as some open water controls, which are pretty much stock tanks full of water. So no vegetation, no substrate. And then a couple of them reserved as a plant nursery. So you can see there's 5 replicates of all these cross designs. So statistically, we have a very robust design that allows us to do a lot of statistical analyses. I will present to you today plots of none of this because it is incredibly complex and very interesting. So I've tried to summarize things as best as I could. From our treatment well and mesocosm experiments that we're doing, we do monitor the traditional physical chemical parameters, BOD, TSS, nutrients. We're more of a metals lab historically. That's what we do. We look at metals in the environment. We do a suite of emerging contaminants, pharmaceuticals and personal care products, pesticides, PFAS, PFOS. A few of those in-house. We do some work in-house with ELISA kits, but most of that work is contracted, as you'll see in just a moment. Then we do a bunch of a bunch of experimental manipulations. So we've completed 3 of those: hydraulic retention time, oxidation reduction potential, solar radiation. Those experiments have been completed. The biological productivity work is something that Zach's working on that he'll finish up next year. So these are our traditional constituents. We do have an on-site weather station, which is extremely important for these sorts of natural infrastructure installations. Physical chemical parameters, nutrients, and again, trace metals and major cations. Our target analytes are done by Dan's laboratory, the University of Nebraska Water Science Laboratory. So a suite of pesticides, a suite of PPCPs, and there's our PFAS. Okay. So I will say that, again, I can't stress enough the partnership with the city of Norman. That photograph of our mesocosm compound was actually taken by one of our city council members during a tour down there. And they've been a tremendous, the provision of resources and space, I can't speak highly enough of. So here's an example of the type of data we're generating. These hydraulic retention time experiments. This is carbamazepine in our summed across the municipal wastewater systems. You can see there's a lot of variability coming in, but we can measure the effluents. We decided after this experiment that a 7-day HRT made a lot of sense. We then followed it up with these aeration experiments where we rolled solar-powered aeration to change that redox potential, a series of shading experiments that cut off the photolysis pathway, the productivity experiments that I mentioned that Zach is doing, and then all of this kind of done on a seasonal basis as well. So different diurnal periods as well as temperature periods. So this is the data. I said I was going to show you only a couple data slides. This is one of them. This is concentration of that suite of PFAS compounds in municipal wastewater and surface water. You'll see that a number of them are below the detectable limits. They're below the practical quantitation limits. Also notice there's a great deal of variability in the raw influent water. So there's a significant variability. Some of them are higher in urban stormwater, SW, than in municipal wastewater. And again, if you look at those regulatory requirements, in some cases, we're actually below them in our influent concentrations, let alone our effluent concentrations. If I take all of those data that we've generated so far and sum them all together, INS, and then each of the 3 experimental designs for the few compounds that are of most interest, PFOA and PFAS, you'll see that we are below that 4 nanogram per liter number in the effluent of all of those systems. So our wetland designs, our free water surface and our subsurface flow do knock them down considerably, but we do see decreases even in the open water controls. So just holding that water in the open water controls. Most likely these are absorptive phenomena. This is not a long-term treatment mechanism. So after the biological productivity experiments, the plan is to actually sample that vegetation and sample those substrates and look for concentrations in the solid phase. So we'll complete this work, sample our substrates, complete development or design and sizing criteria. City of Norman really looking for scaling up to the pilot scale. This guy is Lola. I will tell you, in Norman, Oklahoma, if you put water in a tub in the summertime, stray dogs just love it because they can cool off. So Lola was a husky Malamute that came and hung out with us for a while. She really screwed up our experiments. Okay. And with that, I'll say thank you. The contact information is on there if you see fit. Thank you very much.
So you said economics, did you do anything in economics?
No, not yet. No. There is, as part of our EPSCoR program, we have a partner at Oklahoma State, Mary Foltz, who's doing a life cycle assessment. So the plan is to do a life cycle assessment, which will include some of that work on the mesocosm installations, but the idea being that we'll then scale that up to the pilot scale that the city of Norman is interested in. So yes, hopefully someday.
Thank you.